Welcome. Let's quickly review single variable calculus extremization. So if you have a function like fx is equal to 3x to the 5 minus 5x to the 3. It's a nice function, single variable function. It passes through the origin. We can also find the roots here. So by factoring out, we can say x squared, this is 3, or x cubed even, this is 3x squared minus 5. So there are roots, maybe at the square root of 5/3, something like that. So these are the roots. And if you look at this function, this has grows here like x to the 5. In the large it will go up here, and here it will go down. But what happens in the middle? For that we have to take the derivative and find extrema, find maxima and minima. So if you take f prime x, this is 15 x to the 4 minus 15 x squared, this is 15 x squared, that is x squared minus 1. So we see that there are roots of the derivative, flat points at 0, 1 and minus 1. So they are here. Let's take this, maybe this is 1, maybe this is minus 1. And at the point 1, this is actually negative, right? So this is minus 2. So in this case it's minus 2. The function is here. So the function here is flat. And in this case it's 1, 2, it's like that. So we have already, and then we have a double root here, which means that's actually pretty flat here. So somehow this function has to look like that. So what has to happen, somehow it has to go through that point here, it has to go up here. By the way, to find out whether we have a maximum or minimum, you know that from single variable calculus. We also look at the f2 prime. So we have a 60 x to the 3 minus 30x. So that's 30x times 20, 20 minus 2 minus 2x squared minus 1. So we see also here what happens, say at this point 1, we have a positive value. Positive value means it's concave up. So the function will be like that. In this case, when x is negative, so then this is becomes the negative, and so it's concave down. There will be something like that. But then it has to go somehow like that, and that's a special point. It's called an inflection point here, and then it has to go like that, and then it has to pass through that origin, through that point here, square root of 5/3, and so that's about the graph of this function. It's not very precise, but we have the features. We have all the essential features we have captured using calculus. So this is important. The derivatives, these are the places where we have candidates for maxima and minima, but not necessarily like here. And the second derivative tells us something about whether it's a minimum or not. Okay, we have seen last time that the derivative in higher dimensions is given by the gradient. And there's a principle of Fermat which holds in one dimension. Fermat developed it in one dimension, but also holds in higher dimensions. Let's just look at that. So this is the Fermat principle. Fermat theorem. So if as a max, I just write maximum, max for maximum or min at x naught, y naught, then the gradient of f of x naught, y naught is equal to the zero vector. So this is an observation of Fermat, And let's quickly prove this. It's kind of a nice application of the directional derivative which we have seen last time. If the gradient of f of x naught, y naught is not 0, then what we can do is we can define the vector v, which is the gradient of f, divided by the length. We can now divide by the length and look at the directional derivative. So this is by definition the gradient of f at x0, y0 dotted with b, which is the gradient of f x naught, y naught over the length. It's a computation which we have done last time already, and that's the gradient of f x naught, y naught squared over the gradient x naught, y naught. So that's the length of the gradient, and that's bigger than 0. This length is bigger than 0, and so what this means is then the rate of change when we go in that direction is positive. So f increases when we are there. So maybe here is a mountain like the Matterhorn, and we are climbing here. So this is x naught, y naught. Now let's look at the gradient. So this is the Matterhorn here. We have the gradient points upwards. Remember that? Very important thing. So if we are climbing in that direction, what happens is we are climbing up and we reach eventually the mountain. So the only way that we kind of have a maximum or minimum, if you have a maximum or minimum, the gradient has to be 0. So that's this Fermat principle. And this, let me just write that here. This motivates the following definition. X naught, y naught is called critical point of f if the gradient of f x naught, y naught is equal to 0, 0. So that's the definition, a very simple definition. That's how mathematicians define it. We don't look at cases where it's not defined or so. That's our definition of critical point, and a simple definition, and that's what we use for analyzing now maxima and minima. We come to this next. Okay, I wrote you down 3 important examples. These are prototype examples. These are Morse configurations, Morse situations, which are very important, and the second derivative test really gets into these 3 cases. That's a theorem which is called this the second derivative test. So we assume x naught, y naught is a critical point. Now there are 3 cases. So the case A is if, for that I have to introduce a number. It's called a discriminant. It's a very nice number. So this is fx fyy minus fxy. It's called the discriminant. So you can also remember it like this. It's the determinant of this matrix. fxx, fxy, fyx, fyy. Yes, yeah. So if D is positive and fxx is positive too, then x naught, y naught is maximum. Second case, if D is negative, then x naught, y naught. It's a saddle. So that's what we call a saddle here. So this is max, min. Sorry, this is the min. This is the minimum. This is the saddle. And this is the max. So this is easy to mix up. Actually, did that just didn't not do it by purpose, and then let me do so d bigger 0 and fxx is smaller than 0. That's actually what happens here. Then x naught, y naught is maximum. So maximum, minimum, these are always local maximum, local minimum. So we usually don't say that local, but we mean local, and this is a saddle point. Now this is a very important theorem. It's easy to remember if you know these cases here. Just memorizing it, I got it wrong here, doesn't work. But still, if you want to remember it, there's a nice girl. She's called Minnie. And Minnie has a nice smile, positive attitude. So that's Minnie. And then we have also Maxi. So Maxi not such a happy boy. And then we have also Sadie. So they have a little boy here, and Sadie, maybe I just make it like that. So Maxi, Minnie, Sadie, and you can remember from the smile, you can remember whether it's a minimum or a maximum. We can just assume that it's a quadratic function. This can be justified by a theorem called Taylor approximation. And then there is a little trick here. So you can do A, you can write this as equal to A times something, and then x squared, x plus something squared, and then you want to have that C appearing, and then for C we actually make so maybe this is equal to CA minus B squared. So it's something C minus BA, and that's B squared. So we have CX, no, this is Y squared. So I have AX squared, then you have CY squared, we need 2AXY, so 2BXY, so what do we do here to make this work? That works. So if you take ax squared, that's that, then you have x d over a times 2 times y, that's this. Then you have cy squared, then you have b squared over a y squared, that comes this. That's not here, it's in the back. So what happens is that this is what happens is so that's actually just, so if d is positive and a is negative, so a is positive, so that's actually a here. So a is negative, then it's not. So if a is positive, what happens then? So then this is positive here, and this is positive. So when you do that, you don't have these two numbers. So just make it. And so what happens with the blue number and what happens with the pink number? And then there is the case when D is positive and A negative, and D negative and A positive, and D negative and A negative. So these are 4 cases. Now, if D is positive, then this is positive here. D is positive and A is positive. This is positive and this is positive. So what happens if they are both positive? You see, that's actually just like it's like x squared plus y squared, and so that's the case of a minimum. if d is positive and a is negative, then this is negative and this is also negative here. Because this is ac minus b squared over a. So this is actually equal to d over a. That's a. Now if d is negative and a is positive, then we get the positive here and the negative here. And if d is negative and a is positive, then we get a is negative, then we get a negative and a positive. So these are the subtle. So that's the justification. If you are interested in the proof, this is the justification. We just needed some time to kind of recover that hack, which is kind of just a clever way to rearrange the case. And if there are higher order terms here, then these higher order terms will not matter at 0. But that's just for those of you who are interested in the math. Okay, now the fun begins. We can look at some examples. So that's number 4. So then remember them, I have written them down there. So let's just start with the following one. So we have fx, that's an easier one, is equal to x cubed minus 3x plus y to the 4th minus 4y. So the first thing we are doing is we compute the critical points. So we have to take the gradient and see where it is 0. So the gradient of fxy is 3x squared minus 3, 4y cubed minus y, and we have to put that equal to 0, 0. Now in this case it's easy to see that we can divide by 3 and we see x is equal to plus minus 1. And from the second one we get y is equal to 1. So y to the cube is equal to 1, has only one root, right? So there's not 2 roots. The y cubed function has only, it's a 1-to-1 function. So that means we have 2 critical points. So let's just make a little table here. So these are the points. Then we have the d, we write down the fxx, and then we write down the nature of the critical point. So it's appreciated if you kind of make a little table like this. So we see it's 1, 1 is one critical point, and minus 1, 1 is another critical point. And then also compute the fxx. Fxx is equal to 6x, and fyy is equal to 12y squared. D is equal to that, so 72x y squared, and fxy is equal to 0. So that's it. So let's just see what we have here. In this case, when it's 1, fxx is equal to positive here, so that's positive. Sorry, d, we have to get d. D is also positive, that's 72. So that's positive. fxx is equal to 6. So that's a minimum, right? Because we have at a second derivative test, we have here a positive fxx. Now, if it's minus 1, so actually fxx becomes negative. So this is, d also becomes negative. Actually, if d is negative, that's what happens here. We don't even have to bother about this because that doesn't matter, and we have a saddle. So that's the first example. Okay, let's look at the second example. We have this function. We have to compute the gradient. This is 4y minus 3x squared y minus y cubed, 4x minus x cubed minus 3y squared x. So that's a complicated nonlinear system of equations. If you put that equal to 0, 0, right? Of equations. And that's in general tough. But what helps is factor things out. If if we factor things out, we can kind of factor y out. So we take y times 4 minus 3x squared minus, and that's cube here, minus y squared is equal to 0. And the second equation is we can take x out. We have 4 minus x squared minus 3y squared is equal to 0. Two equations, and still looks tough, but it's doable now because we can look at cases. So first case, when y is equal to 0, then number 1 is okay, right? When y is equal to 0, that's equal to 0. But then we can look in the second equation. The second equation tells us that x times 4 minus x squared is equal to 0, so that means x is equal to 0 or x is equal to plus minus 2. Now the second case, it's case 1. Case 2, we can assume that x is equal to 0. So if x is equal to 0, the second equation is okay, and the first equation tells us that y times 4 minus y squared is equal to 0, which means y is equal to 0 or x is equal to plus minus 2. Now there's a third possibility. So x is not equal to 0 and y is not equal to 0. So then we have two equations like that. So we have 4 minus 3x squared minus y squared is equal to 0, and 4 minus x squared minus 3y squared is equal to 0. Now we have a system, a linear system of equations for x squared and y squared, which we can solve by just subtracting 3 times that from that, and then we get, we subtract 3 times that from that. So what do we get here? If we subtract 3 times that from that, so we have 8. It has exactly one solution. So this minus 3 times that, so that's minus 8. That goes to 0, plus 9. This is 8y squared. So once we take 8 minus 3 times the second equation, that gives us minus 8 is equal to minus 8y squared, which means y is equal to plus minus 1. Y squared is equal to plus minus 1. And then if it's plus minus 1, then we see that x squared is plus minus 1. So that's a tough problem. So, but what we see that x is equal to plus minus 1, y is equal to plus minus 1. So what we have now is 9 critical points. Let me just write them down. Then you have the d, you have the fxx, and then you have the nature of the critical point. So let's look at here, collect all the points. So 0 plus minus 2. So it's 0, 2, 0, minus 2. We have 2, 0, and minus 2, 0. And then we have the points where either we have 1, 1, we have 1, minus 1, we have minus 1, 1, we have minus 1, minus 1, 1, 2, 3, 4, 5, 6, 7, 8. And then we forgot one case, which is x equal to 0, y is equal to 0. So there are 9 points. So let's look at d. So what we have to do is we have also to compute fxx. That's minus 6xy, right? And then we have the fyy, which is minus 6xy, and then we have fxy, which is equal to 4 minus 3x squared minus 3y squared. So what happens here when we have x is equal to 0, so these parts are 0 here, but fx6, that's kind of, then we have fx6 squared. So we just know that's negative. Whenever one of them is 0, we get that it's negative here. So because then we have here something squared which is negative. So this is negative, this is saddle. Now what happens if we have 1, 1? At 1, 1, what happens with the d? So it's minus 6 times minus 6, that's 36 minus, and then 4. So that's 32, so that's positive. And these are all positive because we have always, well, sometimes a little bit less, but plus or minus 2 doesn't matter, so there's always positive here. So that's the just negative here. Here, clear. So this is negative, 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 negative. So we don't care about this. So these are positive, 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 positive. And fx6 is negative if both are positive or negative. So that's actually here positive, negative. That's negative and also negative, and here we have positive, and here we have positive. And what happens if if you have 0, 0, 0, 0, we get this is equal to 0, this is equal to 16. So that's again negative here. We don't care. So this is another saddle point, and this is a max, this is a min, this is a min. I'll show you in class also then how we can do that a little bit more efficiently. Okay, very quickly we will look at them more in class, but these are examples. This example C, this was A, this was B, this is example C, and this is example D. Example C is an example where I show you a little movie, but that's an example where you see kind of this type of problems appearing in physics. What we are looking for is a minimum of energy. So this is kind of the energy of this spring system, and we want to see where this settles down. And it's also interesting to look at the dynamics of this system, which is a differential equation. But what we see here, we see a natural function fxy. And it's no problem here in this case with the quadratic case. So fxy, what we have is x squared plus x minus, so x minus y squared. So x squared minus 2xy plus y squared, and then plus 1 minus 2y plus y squared. And then we have the gradient of f. And then we get minus 2x plus 2y minus 2 plus 2y. And that has to be 0. Now this gives us an equation, a system of equations for x and y. And it tells us, for example, that x is equal to, or y is equal to 2x. And then we plug it in here. And so 2x, we get 4x, 2x. So this means then minus 2x plus 8x minus 2 is equal to 0. So 6x. Then y is equal to 2/3. So what you see is kind of what happens here in this case is that the system settles at the most symmetric situation. It settles at the situation where we have just equal distance, 1/3, 1/3, 1/3 here. Because that's 0, that's 1, that's 1/3, that's 2/3. So that's the first case. So for the double pendulum we have this function fxy is minus cosine x minus cosine y, and the gradient of f is sinus x sinus y. And so this shows that this is equal to 0, 0. We see that x is equal to either 0 pi or 2 pi. So 2 pi is the same thing than 0. Y is equal to 0 pi. And then what happens is we have kind of very interesting situations. We have the situation here when both are pi. So x is equal to pi, y is equal to pi. And if we compute that, we will do that in class. What we see is this is actually a maximum here. And this is the case when we have x is equal to 0 and y is equal to 0. And we have a minimum. And then we have two interesting cases, two subtle situations. So we go down and up like that. So x is equal to 0, y is equal to pi. Or we go up and down. So we have x is equal to pi, y is equal to 0. So these are subtle situations. So this is a very interesting system of configurations, and it's related to kind of the picture is like that. So we have a maximum here, it's a torus minimum, and we have saddle points. If you look at the bagel, right, there are saddles here, and we have a minimum and a maximum. So this is kind of the configuration space of this pendulum. So the equilibria are easy to describe. We have just kind of, we can do that with calculus, but the dynamics is highly non-trivial, and it's still not understood. One sees that there is chaos here. That's an open problem. Probably needs new ideas. I tried that for more than a decade myself to prove things like that, but it's very hard to analyze.